We're doing, hello? We're doing problem number 54. It is the combustion of ethanol, which is depicted by the following balanced equation. This is ethanol. That's oxygen, 3 oxygens and 1 ethanol give me 2 carbon dioxides and 3 water molecules. Completely burned. We need to A, write the reaction using Lewis dot structures. In other words, using lines to depict the bonding pairs and with the lone pairs included. And B, we're going to calculate the heat of combustion for 1 mole of ethanol using the following bond association energies. And this is like a representative sample of what you can expect on the test. I doubt if it will be as involved as this is, because this one takes a little more time than I want to have on the test. But if you understand this one, you can have no problem with anything I'm going to give you on the test. Okay? It's the same basic principle. What is going to be, just before we start, when I go to break a bond, is that endothermic or exothermic?
Exo.
When I break a bond,
It is exo. Gives heat.
Does it take energy to break a bond?
Yes.
Yes. So if I have to put energy in, it's positive, right? So what's that? Endothermic, yes. And if a bond is made, conversely, is it endothermic or exothermic?
Exothermic.
That's where the energy is released. So the negative sign, energy is being taken away. It's released by the process. Okay? So now, first I want to write the reaction using Lewis dot structures. This is going to be, I'm not going to necessarily have to draw the right geometry. I just want to show the bonding interactions. So I will draw it like this. Okay, that will be adequate. I want to be able to show clearly how many of each type of bond is there. That's why you do the Lewis dot structures first. Okay? That's it. It's very simple and straightforward. And I guarantee you the molecules you're going to see on the actual test will be easy. That's not going to be the issue. Now, all I have to do is simple bookkeeping, because the sign for the breaking of bonds, like we've already determined, is positive. It's endothermic. In other words, you have to put energy in. It takes work to tear those apart. So you're going to have to perform the work. You're going to have to put work in. And so now it's just a matter of bookkeeping. And please note the way it's set up. There's several possibilities. The way I have it set up there, I just have it depicting how many moles of each type of bond there is. That's one approach. One I favor more than that one is, I'll stay out here on the outside. I'll go there as 1 mole of ethanol. And what I'm going to use here is ETOH. Because I don't want to have to, it's just a shorthand approach. I could write C2H5OH, but this is just shorter, okay? There's 1 mole of ethanol. I'm going to pull it outside brackets, and then I can start counting the bonds. How many carbon-hydrogen bonds are there in ethanol? I have 1, 2, 3, 4, 5. We just went through this exercise in lecture. Regrettably, I should have picked another molecule for the lecture. Okay, I have, and there is 5 moles of CH for every 1 mole of ethanol. And what is the bond association energy for every carbon-hydrogen bond? How much work do I have to perform? 411. So there's 411 kilojoules for every 1 mole of CH. Okay? Plus, now I've got how many moles of carbon-carbon bonds?
1 more.
Yeah. There's 1 mole of carbon-carbon bonds for every 1 mole of ethanol. And what is the association for carbon-carbon bonds?
346.
Yeah. Plus, now I've got, what other type of bonds are there? Carbon-oxygen? How many moles of carbon-oxygen bonds are there here?
1 more.
What for every mole? Yeah, there's 1 mole of CO for every 1 mole of ethanol. And that has a bond association energy of 358. Okay, and now I'm on to what's the last type of bond that exists? Hydrogen. Plus 1 mole of 1 mole of OH for every 1 mole of ethanol. And there is, for every mole of OH, 459 kilojoules for every 1 mole of OH. And that pretty much exhausts the ethanol. So we've had to go in and break all of these bonds. The good news about the bond association energy, with a little bit of practice, it gives you a feel for whether a particular reaction is going to be exothermic or endothermic, how favorable it is, just based on bond association energy alone. So there might not be a thermodynamic table available for a molecule of interest. This gives you a way of estimating what it's going to be. Yes? Did you have a question? I thought I saw a hand come up. That's okay. Okay, now, what else has to be broken? We have to break all of these too, don't we? The oxygen-oxygen bond, double bond. So it's going to be plus 1 mole, or how many moles of oxygen are there? 3 moles of O2, and there is 1 mole of oxygen-oxygen double bond for every 1 mole of O2, and there is, where is it? 495 kilojoules for every 1 mole of O double bond O. Okay, that takes care of all the reactants. That's all positive. Now we're going to deal with the products. It's going to be minus, I have 2 moles of CO2, and there is 2 moles of carbon double bond, carbon-oxygen double bond for every 1 mole of CO2, and there is 799 kilojoules for every 1 mole of carbon-oxygen double bonds. That carbon-oxygen double bond strength is the one for CO2 exclusively. Slightly different number for the other carbon-oxygen double bonds. Okay, that's my negative, and also I've got the water. How many moles? 3. 3 moles of H2O, and there is 2 moles of OH for every 1 mole of H2O, and there is, what did we say it was? 459. 459 kilojoules for every 1 mole of OH. And now we are done with the setup. The key feature here, regardless of what question I ask you, if you do this sort of a setup, if you make a mistake when it comes time to doing all the calculations, it's not going to be a big deal. As you might have seen, you lose 1, maybe 2 points max for an arithmetic error. What I'm testing is the setup, and the logic should be clear. And the factor label method, this is a great exercise for that. So we can gather all the terms. Now on your scratch paper, you're going to have to multiply 5 times 411. So I'm over here on my scratch paper now. 411 times 5 is 2055. I've got plus 346 plus 358 plus 459. So all the others are straight adds. So 2055 plus, what was it, 346?
358.
358.
459.
And 459. Okay. So we just add these up. 6 and 5 is 11, 28. Okay. Okay. That's 5, yes. 5, 10, 15, 19, 21. 3 and 2 is 5. And 3 is 8, 12. 32, 18. Plus 3 times 495. 495 times 3, 15. 9 times 3 is 27, 28. 4 times 3 is 12, is 14. So I have 1,485. 5 is 13. 7, 3 and 1 is 4. So I end up with equals 4,703 kilojoules per mole minus, and now I have to take out my scratch paper and do the same basic thing I just did with these. So I have 2 times 2 times 799, so I have 4 times 799. 36 is 39. 2 times 4 is 28. 3 is 31. And I have 3 times 2 is 6 times 459. 5 times 6 is 30. 4 times 6 is 24. 8 is 27. So I have 34 and 96. 0, 1. Minus 5,950 kilojoules per mole. equals minus 1,247 kilojoules per mole. Okay, here, this is all scratch paper. What I want to see on the actual test is what you see up here. Okay? This would be an adequate one. I really want particular attention to this part of the setup. This is the detail I'm looking for. The nice part about the factor label method, or what's called dimensional analysis, is it's revealing of the logic. And if you make a mistake, it's easier to track through and find out where it was. Okay? So, are there any questions about this one? If there are no questions, that's